And am I still audible? Yeah, okay.
Yes,
And
I
let me,
hear you.
excellent, because Zoom started giving some messages, but okay. And let me just tell you a bit about Ahmad, although I kind of assume most of you are well aware of all what he's doing, and he's one of the big names in the security research. So any conference, anything like that, it is difficult to not mention Ahmad in one or the other capacity. So he's a professor of computer science and head of system security lab at Technical University of Darmstadt, Germany. And he has leading several collaborative research labs with Intel. So that's from 2012, from with Huawei from 2019. He studied mechanical, electrical engineering, holds a PhD in computer science from the University of Saarland, Germany. Before going to academia, he also worked in R&D like Ericsson, and he's, like I said already, contributing for many years to many conferences and research fields. So editor-in-chief of IEEE Security and Privacy magazine, editorial board of ACM PODAS, ACM TOIT, ACM DTRAP, and for his research on trusted, trustworthy computing, he received the renowned German Karl-Heinz Beckkurz Award. And in 2021, he was honored with Intel Academic Leadership Award at Usenix Security for his research on cybersecurity and in particular hardware-assisted security. So this is very short about Ahmad because he's doing so many things, and I'm very happy that he will give us a talk today about AI and security. So Ahmad, whenever you are ready, please start.
Okay, I am ready. Thank you very much for the invitation first. This is the second time I'm invited to give a talk, and I'm very honored. And I saw a number of colleagues on papers who I know, and I love to see them personally and talk about all kinds of things because research is in one side that's interesting, and I have, as Stjepan in his very beautiful introduction said, I have a lot of different interests, and this is because I watch a lot of movies and I get my ideas from the movies, and then the research assistant, PhD assistant must suffer from it because I comment the next day and say, hey, I saw this thing, I think I can do it better. And they want to listen, they don't want to listen to me, but sometimes they must do it because I am their boss. So anyway, this talk is about my journey or let's say the journey of my research group through the whole AI hype. It is not always in the sense that some of you may want to hear it, because in the last years in Germany and also all over the world, but Germany is always very late when it comes to new technology because we are very skeptical towards new things. In this big AI hype, as I saw that even the janitor of our department is talking about AI and what it is and what is the use of it, I thought, hey, maybe I should look into this, because in 80s, as I was a small student, I was very interested in neural networks. That was a big hype, and end of 80s, and now it is a bigger hype because of the technology that is faster and better. I'm not saying that the algorithmic is always better, but so this is why I decided to look into it. And then I think that AI will extend, as you all know, will extend our existence. The security researchers will always exist because security is related to humans, and humans are sometimes hurting other humans, either physically, but in our case, digitally. Unfortunately, this is our, so to say, the dark side of us, and security researchers will always be in business. However, the AI hype has pushed amazingly the security research, because without security, we will have a big problem. We will not have a pandemic, we will have a digital pandemic. If we allow the big corporation to push us in a direction that we as researchers should not. So I'm going to talk about good things about AI that I think I am doing, and about the bad things of AI that I think I'm doing, and I want to encourage you to join the club. So let's go through some of the things that most of you know, but maybe if you are not familiar with this area, maybe some introduction. So first of all, let's talk about the fact that AI is sold as a universal solution. So as you see, this is an animal which is called the egg-laying woolly milk sow. It's an animal which is a pig. Originally, you can milk it, you can make wool from it, and it also lays eggs. So this is something that is sold to politicians, and a number of colleagues in this area also like it, because we know academia want to have money and funding, and they want to promote their research. This is absolutely legitimate. So, and this is why we should work together. Now, the oil of the whole AI is data. And we know that we have digital technology and it's getting more spread. Everybody's talking about it. So we should really separate AI applications and the methodologies that we know in AI, like machine learning and deep learning. And these are the methodologies that are algorithmic ways of doing things in so many applications, as you see in this small cycle. Some of the applications of many applications that AI is praised for. But here we are going to talk about machine learning and deep learning a bit. And of course, with the focus on their security. And AI should not be confused with these two terms. There are a number of books, a number of researchers who have been doing research in this area for many, many years, as this community was very small, the machine learning community, for example. But now everybody writes something about AI. Many scientists, I don't know, as I said, even our janitor in our department talks about AI. So before everybody comes with another definition of AI, I will skip all the formal definition. I will just try to explain things that I have experienced. And this is a very small experience in the big universe of AI, machine learning, and deep learning. Okay, so now what is about the insecurity and threats of AI? I always say, or at least you know this quote, that when the devil can't come through the door, it crawls through the window. So, and I think AI is also like this. We will talk about it a bit later. So what are the attacks on machine learning? As I said, I'm going to concentrate on those things that were interesting for security researchers, let's say the machine learning aspect, the deep learning aspect. What can we do with it? And what can we, so to say, protect from it? So, as I said, data is the most, we all know, you manipulate the data, and all these algorithms are sensitive to data manipulation. So the data poisoning aspect is very important. Of course, we have also the model as poisoning aspect. And beyond that, there are a combination of data and model poisoning. Security researchers are amazingly, how do you say, they are very innovative. They invent things. As the technology comes in, they always find something to attack it. And there were beautiful papers on adversarial machine learning. These are fascinating things. Some of them I consider as fun. And some of them, let's say, the joy on doing research on something, curiosity, that I am one of them. And some of them are considered as a maybe game changing. So, and we have another aspect that is concerning privacy. So when you have a model, you train a model, and then you get the model, you don't have access to the data. What can you do from this model? What can you extract? Can you extract the data itself that you should not? Nobody wants to give you the original data. Or can you infer something from it? For example, to whether or not you are in a certain class, whether or not you are in a sexual certain class, whether or not you are in a political class. So these are important aspects. Of course, this is important usually in many countries where we have luxury of democracy, and we try to say, oh, our freedom and our privacy, blah, blah, blah. And there are countries that they don't care about that. They say, we take all the data. Yeah, we don't, you don't have anything to say. And in democratic countries, we just do a lot of blah, blah about that. There are, of course, laws about it. That is interesting. But we have also cameras on every edge of our cities. Go to London and you will see, when we talk about privacy, this is absurd. Okay, so reality is always different than the papers that we send to some conference. Okay, so now as you see, some of these attacks are during the data, so to say, training. Some of them are sort of pre-training, some of them are in training, and some of them are post-training. Now, as you all know, there is something that, for example, very much hype in US, but also coming to Europe and discussed everywhere, and that's the coded bias. And I think you all know that more and more machine learning, whether or not people know what they are doing or not, are integrated into decision makings. So this is one thing that I truly believe will lead to digital crisis, to a pandemic that will concern all of us. We know it, but we still accept funding from or some project financed by Facebook. Yeah, if we are doing ethical, if we talk about ethical science, we should also be consistent and not work with these people, because these people are not working for us. So why? Because if you see, for example, the US credit market, but also in Asia, go to Hong Kong, many of these decisions are done by some automatic process, whether or not you call it AI or machine learning or whatever. There are disparities here. There are discrimination and real discrimination here. And it is coming also to other countries, like in UK, they were always like this, but they're coming to Germany and other places. Now, if you have an Amazon and you have 500,000, I don't know, application to work in Amazon logistic without any break, without any union, okay, then the automatic procedures are done for recruiting. And that is, of course, a catastrophe, because all of a sudden somebody leaks the information that this is biased against women. Of course, these algorithms cannot always be fair, because fairness is a big research topic itself. And then the most vicious company that I know, at least beside all the weapon companies, is Facebook. And it is amazing that the press is always interested in some middle manager, someone in a middle management, like this lady, who just came out after several years earning millions of dollars, coming out and being a whistleblower and developing conscience, saying that these algorithms that Facebook is using, as they call it, it's the wisdom of crowd. So that means they are tuned in such a way, as we all know, that if there are more and more negative hate messages, they should also be classified better and nicer, so that they can escalate the hate. If it comes to, we all say, oh, social media hate, blah, but we tweet a lot of junk about, oh, look, my paper is published here, or your paper is not as good as my paper. Academia do it as well, so we are not the exception, but we should also open our eyes about the development around us, and not always looking, oh, there is a funding there and I have to do it, and then I do something that I call it machine learning for some company that is doing really evil things, and we all know it. So the wisdom of the crowd means that, okay, if the crowd says like this, it must be okay. Yeah, but we know from the history, India, British went there, and several hundred years they exploited that country, and they're still talking about Commonwealth, and many other countries in Middle East, they exploited everything, and they are still thinking that they are a kingdom. And now the wisdom of the crowd is, we are Commonwealth. you are still having a queen. And if the wisdom of the crowd is that go and hang someone, this interpreted in digital scenario is what is now these algorithms are doing, because these are not really complicated algorithms. They are doing classification, clustering, and all this kind of stuff that we know, but we are helping them, okay? Manipulations of data, you all know these examples. These are really standard examples, but I want to just explain to you the critical points that I personally see here. One of them is, okay, you have adding a noise to a stop sign will prove the algorithm, the machine learning algorithm can be fooled to, let's say, identify it as a maximum speed sign. Okay. And then I was asking myself at that time, as these papers come out, and they were celebrated, I said, why people write paper about this? Because we know that if you manipulate the data, then you get a wrong output. So what is the point here about the scientific approach? And I think these are very good. And I was mistaken, because I think this example, simple example, and many other examples, as you see here, for example, that the Google search machine for pictures, it was fooled to show weapons, so by digital manipulation, as for example, helicopter and aircraft. And this is for law enforcement agencies. That is important. Yeah. Okay. It's the matter of definition. In US, many people have guns, so what's the point? But for other countries, this is the point, yeah. Or things that, for example, with a physical obstacle, by putting a tape on a shield, you can manipulate the data. The interesting aspect here is maybe as people done it for many years ago. I think it was 94, 95, where there's a paper, and that paper was very much debated, where people put a makeup on their face and could not get by surveillance camera because they were just phased out. So these obstacles are important, physical obstacles, because if you can fool all these algorithms with physical obstacles, this is not scalable, but it is interesting. It is deception. Yeah. So, and then we have the same thing that Tesla's camera was, so to say, the image recognition of Tesla was kind of fooled. Or here, the group at CMU, from Lujo Bauer, this is this guy, Lujo is a colleague of us. And here, by putting a patch, this is the example, as an example, this is, for example, these glasses, they fool the algorithm that these people in the upper row are recognized as the people in the lower row. And something which is the most easiest one, here you see a kind of, it's called the typographic attack, where you put an iPod on, so to say, just the writing and post it on Apple, and you get iPod instead of yeah. So these are examples showing, okay, you can fool these algorithms. That is nice. They will become better, but they will never get perfect. There are always a loop, a hole there to get in from security point of view. But it is important to know that we should not rely on these things, especially because these things are not about Apple. They are going to do face recognition for people. They are going to judge people with these things. So here we come to the next thing that I think it is interesting as a play, and I always show it because I did it with my one of my postdocs, Hossein. He did that for me, and we discussed that a lot. What is the actually? I just show you to you first. This is the deep fake. As you see, in my spare time, I will sing Bella Ciao for you. Okay, you will see that it's that B, but why I am showing that to you is what is the threat here? We need to, this is also something that is completely missing. What is the threat of a certain technology in a certain context. In Germany, there was a big consulting company that all of you know made a study about companies in Germany using AI, and more than 60% of asked CEOs and CTOs said they really don't know what is the use of AI for them. Yeah, because the big industries like Google and Facebook and Amazon are pushing this technology that you and all other companies and enterprises get a bit kind of dependent on their algorithms, on their libraries, on their hardware for doing things that they may even not need. But this is the trend, and many people go in this direction, which has good and bad sides, as any other technology. But this is a bigger thing because the current conventional standard security measures cannot be directly straight applied to these algorithms because they are not deterministic in general. And that is one of the problems. We either need new methodologies, as I'm going to try to, hopefully there's time to show it to you, or not. So deepfake is interesting, but what is the point with deepfake rather than being nice? Yes, social media, but what is the threat to our society? Because our society is not only social media. I just want to remind you that deepfake is, maybe those of you who are older than 30 or 35 years old remember this picture. This is UN many, many years ago, 2003, where a savage war was initiated by US government after 9/11 by claiming with this picture at UN, of course, this is all, of course, the theater, but this picture was shown as evidence for mass destruction weapons in Iraq. Hundreds of thousands of people died because US military wanted to just get the oil. And this Mr. Paul lied to UN, and everybody who were allies knew that he's lying. So this picture, if a student of mine does this picture, he or she is not allowed to show it at the conference. But this was a fake news at that time. There is no deep fake here. So why I'm showing that is that governments are afraid of this deep fake because it may be a technology that is put to everyone's hand and everyone can do it. That is the problem. If they want to do it themselves, it's no problem, because here you see the, as I call it, shallow fake. It is a shallow fake, but it started a war. So we need to also in a bit think about it, all these things a bit more critical. So I come to another thing, which is Zoom fake. So I just invite a friend to show us her presence. As you see now, we see Chancellor Merkel, who is visiting us and can join to Zoom. As you see, she's not talking because there is someone behind it who has a masculine voice. And if you change it to Steve Jobs, then say something.
Hello. Hello.
Okay, so
Can you hear me?
This is not the voice of Steve Jobs. So what we are working on that is to put the fake, so to say, the deep fake voices on that. And this is what our students are doing. Why I'm showing you that? Because this is interesting from one aspect. Think about cyber criminals in the areas that I personally am very interested to do something, like pornography, child pornography, which is a taboo place. Nobody is really willing to go there. And these technologies allow you, because they get pictures, they get videos, the law enforcement agents. And believe me, this is not something that you can look at. So, and then when these people suffer from it because they have to look at it and to analyze, is this person in this picture and is also in another picture? To correlate them with each other. And if this technology gets, this is just image recognition, image computer vision, yeah? So to say, it is matrix multiplications. But if this gets very, very sophisticated, so that those people who are spreading child pornography in the network, because they are one of the most sophisticated ones, they don't want to get caught because they are sometimes in a big job, they are from a good family, they are from places where people respect them, but they don't know their dark side. And if they use this technology, then we have no chance to get them, unless you put undercover agents really within those teams. So I show you this to say why we are working on that, because I see a societal aspect of it because of the technology, not just because of machine learning. So thanks a lot, Jay. So now I'm going in the last part of the talk. I'm going to talk something about more what we have been doing as research in this area to see the advantages of machine learning, specifically federated learning, and also to see what we can do for machine learning and federated learning in this sense. So federated learning, the basic idea is you have many clients and you have an aggregator, a server. The clients have the data locally, they train their model locally, and they send a kind of update of the model to the aggregator. The aggregator puts them together, or aggregate them as the name says, and sends the update back. Why doing that? Because in collaboration, the models become more sophisticated because each client has maybe a different size of data set, access to more data for a certain task, and some other they may not have. We will come to some examples. And the fact that they do not need to share the data with the aggregator, that is very important. This is a kind of solid basis for privacy aspects. So I don't want to provide my data to the aggregator. I just want the aggregator to aggregate it and make my model better. So benefits of federated learning is, of course, the aspect of privacy. It is not guaranteeing privacy. It is a good, it provides privacy enhancing in the first place. There is a hardware efficiency here. It means that many clients, they use their own hardware, so the server does not have to have all this hardware performance. And of course, there is a performance boosting, which is also debatable. In some models, you may be more efficient in a centralized solution, but centralized solutions are not good because you give the data to the server and the server is a single point of failure. Here as well, but only the aggregation is attacked, but not the data. So federated learning applications are, I mean, there are a lot of them. So you can use it for autonomous driving, for example, improve image recognition. Every car is a client here. We are now working with a number of colleagues in mechanical engineering in the sense of design of electric cars, because they want to know how they can optimize their cars by getting information from the cars. I just didn't put it here, from the clients, but the clients, what is their consumption, how they drive, and from that information, they can design cars that are more efficient, or for word suggestion. Then there are applications that I'm going to talk about 5 minutes or 10 minutes on IoT anomaly detection systems that we used it with it was a big project with Cisco to see if machine learning or deep learning there was of use. Medical assistance, this is a project that we do with Intel on, so to say, on collaborative learn about brain tumor segmentation that should assist the doctors in their so to say, the approaches. I say assist because things can go very wrong if you rely on that. Yeah, you should not rely on that. You just assist. And then there are also something that we did recently will be published in NDSS 2022 on sharing the cyber risk intelligence that one of my postdoc was Hossein was leading that. So I will go. So first, I will start with IoT anomaly detection, explaining to you what we have done. So we started with this research as we had, as I said, a big project with some industry partners, amongst others, Cisco, where there was a lot of heat on IoT bots. And that was very interesting from, let's say, from curiosity point of view, what can we do against IoT bots? So since my group is doing a lot in IoT research, we started to look into aspect by looking at, for example, prominent IoT distributed DOS malware like Mirai, and I think most of you know it, but also there are derivations of Mirai. So this attack was in 2016 or 14, between 2016 is very interesting because many devices were connected to each other. They were infected, connected. And then the first version needed, I don't know, 150,000, this is our estimations. And the second one, even up to 1 million devices were concerned, but 300,000 is again estimation on infected devices. This is the attack, which is called Hijimi. And what was interesting is that these attacks could send a lot of requests to the backbone networks of big providers, and that is like Netflix, Amazon, or I don't know, Spotify. And imagine if Netflix is down in US and half of US cannot watch Netflix, that is bad because they can go nuts under pandemic and they have also guns, so it can lead to other problems. So this is why we started to look into it and say, okay, well, how does Mirai work? That was the first thing that we started to understand. Okay, it uses really a number of different attacks put together. It scans networks for vulnerable devices. Then there is a command and control server. It has several components like listener and loader, but this is not important. It is important that once the device, the code is loaded to a device, for example, because they have open ports and they have default passwords. So you can scan the network, find the device, and then load the code. The interesting part of the Mirai is that when the code is loaded to the device, the code closes the ports, the open ports, to avoid disturbance by other Mirai instances or by any other malware. So the malware is kind of intelligent, yeah? And of course, there is a back and forth with commands, and then you access, so to say, you attack all these devices, send requests to a victim server. So the adversary model and assumptions in this scenario is that IoT device can be compromised. So usually these IoT devices are connected to a gateway at home, for example, yeah? But IoT devices can be compromised and gateway can be compromised. One other assumption is that when you have a benign device, so the device, when it is released from the factory, it is benign. And when it is installed at home, it is also benign. We do not assume that devices are malicious from the beginning, because if Amazon provides malicious devices, then you have no chance to do anything, and you may be able to detect it, but you cannot do anything against it at the beginning. And the goal is, of course, to detect the adversary based on behavioral change of IoT devices. So when we say behavioral changes, then I would like to introduce to you what we did, which is called diodes. It's based on federated learning, and I would like to explain how it works. So why don't we use intrusion detection system as we know it? The statistical typical intrusion detection systems for IoT devices provide a lot of false positives. That was the first reason, because we tried it out. There are tremendous number of publications in that. The second thing is that these devices have very scarce communication, so they do not communicate the whole time. And the third thing was that we did not know much about all kind of devices, so we needed, and we could not model each device, because some of the intrusion detection systems are based on signatures, and signatures can be good, but as soon as you know the signature, but as soon as you don't know the signature because the attack is new, then you need to update your database. And we know from all virus scanners, the conventional virus scanner, this is not a good idea. So because of these things, we started to think about, okay, let's do the following. We first ask ourselves, what kind of assumptions can we make about these devices? So we first said we don't do much assumptions about it. So that means we don't consider that these devices have hardware trust anchor or security architectures or very complex cryptography. We just want to know their behavior. So for that, we assume that we have a secure gateway, because at home you have it. And we assume that this gateway is not malicious, because if the gateway is malicious, there is another problem with that, okay? Then we have an IoT security service provider, yeah? And as you see here, there are also many other security gateways, as you see here. So this is about a large scale network. And then this service provider has kind of fingerprint of these devices. What it means, we will come to that. And there is also a profiling of these devices where federated learning will help us. So that means the federated learning is that all these gateways send their modeling of the benign behavior of the devices to the server. This is aggregator. The aggregator has also device type identification. I will come to that. Why device type? Because many schemes before, they try to model each device. If you model each device, it is huge complexity. So we thought about, how about having equivalence classes of devices? So this is what is device type. So for example, let's say IP camera of many companies, when they have new versions, the hardware does not change much, only the software changes. And depending on but the behavior of the device and the standard protocols that they use, it also doesn't change. So they will fall all into the same device type. Okay. And that device type has, of course, a behavior profile, the benign behavior, not abnormal, benign. So, and then in the fifth things, after the model, so to say, this profile is distributed to back to the security gateways. Each security gateway updates the profile, and when there is a behavior, like for example, in case of Mirai, it detects anomalies based on device type specific profile. And then to know more details about it, let us talk about, I don't go through the all the contributions, but the important thing is that our question was, what do we do if the attacks are unknown to us? Yeah, so we are going to model the benign behavior of device for device types. And then based on that, we decide if something, a big attack is coming. So it's a kind of seismometer, like for denial of service attacks in IoT networks. So how do we make the device type identification? Here are our standard methods. So we understood that IoT devices display background traffic patterns that can be used to identify device types. So here you see that based on this periodic behavior pattern, we could identify devices. Here you see a picture of, for example, of D-Link IP camera, where a various number of protocols are used. You see these protocols here in this axis. And as you see, the communication protocol, when the device joins the network towards the server and towards the security gateway, is periodic. And here you see two periods. So what we did, we empirically checked 33 devices, popular devices that many people have their homes or even offices. And then we understood that they have periodic behavior. So then the packet flow is digitized. Then there is a standard signal processing discrete Fourier transform to understand the periodic behavior. But then to see what is the real periodic behavior, we use autocorrelation to have stable periods, because there are also some, so to say, fake periods. And then after that, we take this periodic behavior or take this period and build features around this period. And from this set of features, for example, these features are the number of periodic flows in which protocol layer, mean periods per flow, so standard deviations. So all these things that you see, this is not done automatically. What is done automatically is up to the period. And here we start to see what can we define as a feature around this period. And that was some of the examples. And for that, we use a very simple K-neighbor classification algorithm. And so in that sense, we have a device type prediction. So what is this for a device type? Yeah. Now, we evaluated that, as I said, on 33 devices, and we got very good results. And we did that long term. So that means over 3 years to measure all these things, collected data, and currently our data is used also by other research groups. So now to the second thing. So this was device type identification, not device type specific anomaly detection. And for that, the hypothesis is that anomaly, of course, is different than the normal behavior, but we model the benign behavior. So anything which is not benign is anomaly. And of course, we have to bring the false positive down. And for that, we use gated recurrent unit algorithm, which was kind of very much hot research topic, at least at that time, and it's still a hot research topic, is use cases that was this algorithm was considered for, where, for example, text prediction or correction, it learns a sequence of words and predicts the next one based on the history or probabilities of the last so to say, subsequent words. And the idea is that the communication protocols are also like language. So we transfer these communication protocols to a symbol set that can be processed by GRU. So that means these GRU models can also learn normal network things, network packet sequence. And then we consider what is the probability of occurrences of occurrences of a certain packet based on observed packets. So this is what they do. And here again, the packet sequence, we detect the packet sequence from the network, and then there are some characteristics that we extract, for example. These are, again, things that are not done automatically at the beginning. This is manual. Incoming or outgoing, bin of port, it's like labeling, yeah? So bin of, so for example, what kind of port it is it incoming, is it outgoing, what kind of length of the packet we have, what kind of encapsulation we have, what is the packet inter-arrival time, and so on. And then there is a symbol mapping, and then the GRU model is just plainly applied to that, and there is an anomaly which is based on the probabilities. So this is the complete usage of machine learning, especially the recurrent machine learning in that sense. So, and for that, sorry, it was too fast. For that, we could have very, very good results, and also Cisco guys were surprised. We were surprised as well. It was a lot of work, engineering, but so this is the use of machine learning in a specific case. So that makes it interesting. So we started to do other things like how do we model, for example, cyber risks. So I don't go through that much. I just want to tell you about 2 minutes that cyber risks, we know it from threat intelligence analysis. This is a very complex thing that maybe some of you know about it. So how companies do threat intelligence analysis? There is a complex procedure that is involved to report and monitor and profile and collect the data and then analyze the data to see what kind of threats are coming to our network or local computers in an enterprise. However, we didn't look into that because this is very complex in the sense that companies do not provide that openly and also don't provide this information to other instances or other companies. So we started to think about cyber threat intelligence and thought, okay, it is difficult to manage. It is needs kind of automation if you want to make it simple. And of course, it is a privacy aspect because nobody wants to provide you the data. So we said, why not using federated learning? And here we do kind of risk model. That means end users use their phones. Their phones have a software that has no higher privilege because most customers are using apps. These apps have a wrapper. This wrapper checks for some anomalies, like is it the phone jailbroken? Is it there is an emulator? We will come to that. Here you see here is the user, and there is a risk monitor in that app. This is used by financial institutions. So we connected. We had the privilege to work with a number of financial institutions in Europe, and we convinced them to use this because they would not provide the data. So the risk monitor monitors the risk. And these are simple risks as, for example, credit card companies do. If you always pay in San Diego, but once you pay somewhere in Tijuana, they say, okay, Tijuana is near to San Diego, that's okay. But if you all of a sudden pay with your credit card in Colombia, then they say, hey, this is maybe not good. They block your credit card or they inform you. Here it is done automatically by looking at, for example, is it a jailbroken? Is that code there is a suspicious of code injection? Is there any emulator running? So these are the things that you do not need operating system privileges for. And of course, this risk management, every company has it, and they do this risk. And what we did, we model the risks. So as soon as we have the modeling, then every company, every service provider has its own model, and in the federated learning scenario, they can manage that better because every company has a set of risks, and then the aggregated model has, so to say, a richer set of risks. And if there is a security-sensitive operation, as you see here, like login, then of course the risk management is getting better without the companies revealing the data. So again, and the risk level is low, medium, and high, because if it is high, or of course false positive, if it is high, the user is informed there is something wrong. Also, the company is informed. Okay. So we used indeed around 24 million data from 24 million users. This is the only interesting thing about that, beside all the engineering work. And of course, some interesting contributions in the sense of realizing a threat risk model on mobile devices. So, and this data was collected over 6 years. And you see, we have here, we call them here ABCD. There are 9 different financial services or payment or insurance services. They were involved in this thing. And this is some evaluation. As you see, the federated model is always very good. It performs very good. So the last thing that I want to talk about, the last 6, 7, 8 minutes, hopefully, and then you can finish it, is what are the challenges that we are considering now? Because there are the number of algorithmic challenges, there are a lot of application-oriented challenges when you use federated learning or any learning algorithm. And here we have different aspects. First of all, we have different systems, different devices. We talk about edge devices. For example, Facebook and other companies want to push more to the edge devices because they don't want the teenagers to wait for some funny pictures wait long, because then they don't use that app. So they want the edge device to have an extra processor to do these things for their target group. But this is one side. On the other hand, for a real good usage, except this, oh, I have a funny picture, like automotive scenario, like maybe an energy saving, you have heterogeneous systems and they have different computational and storage capacity. The next thing is the statistical heterogeneity. What does it mean? It means, is the data identically distributed, or is the data non-IID? So if it is not identically and independently distributed, how do we model those data? Or when the behavior changes of the clients. The aspect of fairness is very important, and federated learning makes it more complicated because it is again federated. Yeah, think about the crowd, the wisdom of crowd, privacy concerns and security concerns that I mentioned at the beginning, and I want to talk about these two very short. So the attacks on federated learning, data poisoning, we know, data and model poisoning, we know, and of course, privacy attacks that can be done from the server point of view. As I said at the beginning, federated learning provides a good and solid basis for privacy, but it doesn't mean that it is fully private in the sense that you don't get any leakage. The model updates that are sent to the server, it has been shown, and of course, in other, for general machine learning as well, that they deliver information about the data that you may also either do information inference or you do a data reconstruction. So what we consider here as very important is the data poisoning aspect first. And in that data poisoning, the aspect of backdoor. Why backdoor is interesting? Because it gives the adversary the control over the outcome by manipulating certain parameters. Here you see that the training goal, here I just want to show you the normal procedure is the optimizing the model parameters. That means the weight. So here you have data, then you have your model, and then there is a feature set extracted, there is a prediction, there is a loss function, and you have, of course, a label as input to the loss function. And then you try to optimize this loss function and get, so to say, your improved optimized weights. So this is the normal procedure. Now the backdoor starts that with the fact that the data is manipulated. But if the data is manipulated, for example, these labels, yeah, then there are normal procedures that can cut this out, like average this out. But the real problem is that when you start to manipulate the loss function through changing the parameters in such a way that the loss function is adversarial, and that is where the weights are poisoned. And then when the weights are poisoned, of course, you can control your output. Now, this is what we were very interested in. So because backdoor is always, also in cryptography is very important. And here we also were in founder. So, and this is why we started to think about how we can prevent these backdoors in federated learning, because there were several attacks and we wanted to have a more general solution because many solutions, defenses were only customized for that specific attack. So here I want to show you flame in a geometrical sense. So assume that here you have this global model as a vector at time t min -1. And then you have these weights. These are the model updates coming to server. Then this is an outlier. This is a manipulated weight, so to say, a vector, which is under the control of the adversary. But the distance to the global model is big. Then we have another outlier, another adversarial vector, which has a lower distance, and another one which has even lower distance. So as you see, there are different flavors of these sampling of the adversary. So we want to prevent all of them. How do we do that? First of all, we look at the angle of this vector to the model. So if this angle is too high, we just cluster it out. Then we come to the place where the sensitivity, this is ST, we call it sensitivity, which is the Euclidean distance, the median of Euclidean distance between the updates and the global model. These are for vector W'2 and W'3. What does it mean? This is called model clipping. We just reduce the length of the vector so that they are just similar to these updates that are, for example, benign. Yeah. And the last thing that we do is to add a specific amount of noise to average out any control, to get the control of the adversary out of the model, because the noise is random. And this should not be misplaced with differential privacy. It looks like it, but it is an amount of noise and which we formally show what is the lower bound for this noise to be added at time t, because at time t you will update the system. So this is how we try to take the adversary's control out by, maybe I'll just show it here in a big picture here. So you have all your models, assume that these models are manipulated. Then there is a model filtering, as I said, it reduces the big ones. Then there is a clipping, it reduces you see the color has changed. It reduces kind of the effect of the malicious ones. And then the noising that takes the control of the adversary at the end out of the model. This is the idea behind it, and it can also be used for untargeted attack. However, even doing that, it could be that so this model works for when the distribution of the data is identical and independent. That's very nice. But and it covers also some non-IID distribution. As soon as it starts to become too much of non-IID, this model may cut some of the benign models out of the performance, and that is not good because the performance of the model is based on the benign model. So here, a solution to, so to say, to mitigate this problem is in an upcoming paper at NDSS 2022. Okay, so the last thing is privacy on top of backdoor mitigation. Assume we have backdoor mitigation, and then we want to have privacy on the aggregator. That means the aggregator should not see the updates. How could that be? So it means it should operate on encrypted data. Fully homomorphic encryption, too inefficient. Maybe something a bit more efficient, and that is the typical, let's say, typical secure multi-party computation. So that means we share all these updates among two servers that are not colluding. So it is the adversary model is called honest but curious. So the adversaries are not active. If it's active, there are also solutions for it, but it's even more complex. So because the aggregator just wants to know what is what, but if they actively do it, it's of course another, we have to have a malicious model for do the secure multi-party computation malicious model. So why we do that? Because I did 10 years of this research, so applying crypto in practice, and I wanted to know, does it work? And I can tell you, this is typical secure multi-party computation, you share the updates between two servers and then run a specific protocol. And then after that, you can get the result, and then you send it back, and the shares will put together, and then you can have the aggregation result. Now, if you use this, it is 80 times slower. So for 100 clients, for different benchmarks, from 80 to 100 times slower than in a normal case. So that is not really advisable. So those who are writing papers on secure multi-party computation should really, really think about a lot of engineering to make this practical. So with that, I come to the end of the talk about the current work that we are doing So I explained to you how we use federated learning for improving security and how we used security measures to improve the algorithmic aspect, because all these algorithms are without no security. This is good for us, but we need new measures to fight against the insecurity of machine learning algorithms. And what we are now doing is that instead of secure multi-party computation, we put on clients and on server, we call it enclaved computing. That means trusted execution environments or secure hardware like Intel SGX, depending on which adversary model you are defining in, so that you have privacy, so that the model updates are running in a secure environment by hardware, but also the data, the models on the client side are also protected. This is much more efficient than secure multi-party computation or differential privacy, because differential privacy is not useful because of degrading the accuracy. And we are working on detection of untargeted attacks in FL, and also defenses on something which is called split learning. Split learning is also another way of collaborative learning, where you divide the computation between, let's say, the server and the client. Yes, and thank you very much for your patience. It was too long, and I hope that I could motivate some of you.
Thank you very much, Ahmad, for a very nice talk. So now it's time for questions. Do we have questions? Let me see what the Slack says. Slack, nothing. So the easiest, if you want to ask question, is you can write in a chat so that I can read it and everything. And while waiting, let me start with a question. So you said you are also looking in split learning. Split learning is just similar to federated learning, but the difference is that part of the computation is done also on the aggregator side.
Yeah, it's divided among the parties. Yeah.
Mm-hmm. So
it's still collaborative learning, but it is not like every client does the whole computation and sends it for aggregation. It is divided among different parties, and we are looking into attacking it, because it seems that to be even simpler to attack than federated learning.
Really? Simpler to attack? I
think so.
Oh yeah. Intuitively, one would say it should be more difficult to attack, because there are, more places.
Because the problem is that in federated learning, for example, we need to assume that of course it depends on the adversary model, but in federated learning we assume that at least more than half of the clients are benign.
Mm-hmm.
Yeah. So here in split learning is a bit difficult to do it, because it depends in which scenario, but it could be at least our first, for simple attacks, it seems that it is more sensitive to simple attacks, but maybe if the system is under another adversary model in a more complex system, maybe the attack will also become more complex.
Cool, thanks. So looking for questions, people.
No questions, that's good. Nobody listened, that's very good.
Yeah.
I have one question, Ahmed. Like you mentioned about using like the hardware enclaves, like maybe Intel SGX or secured enclaves, right? But they also have been targeted by side channel adversaries, right? So
yes.
Any comments on that, like in this context?
Yes. So again, it depends on the adversary model. Okay, so if you consider the attack scenario that I mentioned for secure multi-party computation, let's start with the server side. The server side is honest but curious. So in that model, if you use a trusted execution environment, so let's say Intel SGX, curious means you don't do an active attack. It is honest, you don't run the protocols, you just see the computation. If you cannot see the computation which is running inside the enclave, that is much, much more efficient than secure multi-party computation. However, if you go to the active attack scenario, that means you can run a cache-based side channel attack on SGX, which is in many cases have been fixed in the sense that either the, for example, the attacks like foreshadow is fixed because now they flush the L1 cache. But if you assume that all these cache attacks are not fixed, yes, the server, an active adversary server, can try to do a side channel attack on SGX. Now, on the client side, the client is either benign, so it has no interest to attack the TEE, the trusted execution environment, or the client is not benign. In that case, of course, the client can try to access, to read something, to get the model, yeah, because using trusted execution environment helps to hide the model, not the data. An adversary that has compromised a client can always try to manipulate the data itself, yeah? So the model is inside the TEE, but the adversary can always manipulate the data. So now the question is there any, if SGX is not fixed in total, because SGX is using cache, shared cache architecture, which is clearly delivers some information, has some information leakage. There are, of course, new architectures, not by commercial, but more on the open source area, like RISC-V, that provide side channel protections. Yeah, there are a number of research projects that are looking very promising. Amongst other, our research architecture based on RISC-V, which is called CURE. There is also other RISC-V security architecture like Keystone from Berkeley, like Sanctum from MIT. All of them have their advantages and disadvantages. Of course, our design is the best one. So, but I just want to be modest. I just don't tell it here so often, yeah. But no, seriously, yes, this is a problem, but not in the honest and curious model, because we are concerned about the privacy aspects on the server side. And in the honest and curious model, you are much, much more efficient than secure multi-party computation, or fully, semi, not fully, I don't know, fully homomorphic encryption. Yeah.
Thanks.
So thank you.
Thank you again for invitation. I hope one day we can see each other and discuss these things in person.
Thank you, Ahmad, once more for a nice talk, and yeah, hope to see you soon.
Yes, thank you.